answer's right here. We better send the knack back, right? Whatever you thought you said is garbage. Resend it. Now over on this end, we get a knack back. Well, what the heck? With what we have now, with only the logic that we've implemented so far, which is bit error checking, this has to result in what over here? The server retransmits the knack, right? So, got a knack coming back, the knack arrives okay, it's received, decoded, okay, we understand. That's a knack to what? What's actually being knacked there? Come on, guys, this is the easy part. It's not going to get really hard for about a couple weeks. Is this correct? What?
Data.
That's not exactly the answer. This is incorrect. I'm lying to you, and I did it because I'm sneaky and I'm trying to catch you. So, we send this knack back for this. The first thing that has to come back is an knack to this. Then comes the knack that got garbled from up here. Now, with just what we've implemented so far on the client side, do we know what's going on? I just got an ACK and a NAC in succession. So is our implementation okay? Is our logic so far sufficient to provide for recoverability, resiliency, dependable data transport? Somebody's nodding, but I don't think they really want to. No, it's not. With just what we've done so far, by the time this sequence happens, and I've left out some stuff up above, but it doesn't matter. By the time this sequence happens, on the client side, we have no idea what's going on. Can't possibly. Not enough information. So if you don't have enough information, what do? You add more information. Here's the logical implementation of our bit error checking. The send, for the send packet, on the left-hand side on the top, I don't know why that's a K. I screwed that up. It should be SND packet. Maybe it's sync packet. Throw it away, forget it. Send packet. We make the packet, we encapsulate the data, and then what do we add? We add a checksum, a hash value, so that it can be checked by the receiving end. And then we send the packet. And then the FSM here, waiting for the call, changes state, and waits for either an ACK or an ACK from the other side. And it just, that's it. Now we're here, waiting for something, right? On the receiving end, we're waiting waiting for a call from below. Call from below, what does that mean? We're waiting for notification from the transport layer that a packet has arrived. The particular socket that we're interested in. Right? Our state machine is waiting, it's spinning on a socket. So it gets woken up, we've got the packet, we take a look at it, all right, and at the very bottom, where I need my pointer, we're over here now, we extract the packet, okay, if it's not corrupt, then we extract it, we deliver the data to the layer above us, and then we send an ACK back. But if it's corrupted, now we're on top, what do? Decode it, look, and then we send an ACK. That's all there is to it, pretty simple. What, 4 lines of code? Piece of cake, walk in the park. Okay? But we've already determined that it's insufficient. Oh, shucks. Okay. Operation with no errors. The delta sign, by the way, this is a convention that they're using. I don't particularly like it, but we'll leave it. The upside down V. I mean, you've all taken math, right? Some degree of algebra? Yes, no, maybe so, maybe not. Delta is usually used formally to indicate a difference, right? In this case, they're using it to mean no action, no op. I don't like it, but I don't want to throw any confusion in. It should actually, to make it perfectly legal, that should be delta equals 0, right? So we wait for the call from above, and it's waiting. Both sender and receiver FSMs are waiting. The upper layer sends the packet to us. We build the packet, the datagram that we're going to send. We send it over to the receiver. The receiver decodes and says, no problem, right? It's arrived at the other end. We compare the checksums. They agree on the top there. So on the bottom, we extract it, we deliver the data up, and we send an ACK back. Right? Meanwhile, the other side's waiting for the ACK or NACK. We send the ACK. We're done. Everybody's happy? No problems. Now, error scenario. We're still waiting. On both sides, packet comes down, we generate the checksum. All of this looks the same. We send the packet, it arrives at the other side. And the event is that our, I just drew a blank. Somebody help me out. RDT, what the heck does that stand for again? Reliable Data Transport. Our RDT state engine is sitting over at the other side. It gets, the event is it gets the packet, it decodes, it disassembles, it demultiplexes the packet, checks the checksum. Checksums don't agree. We send the NACK. It gets over to the other side. It's a NACK. And what do? We resend the packet. See how that happened? Any questions?
Is there a chance that the errors occur again?
There is a chance that the error occur again, yes.
So in that case, how can we ensure that, for example, there might be endless errors?
There could be, yes. Have you been reading ahead?
No, I just imagine because sometimes.
You're exactly correct. But in our logic so far, we haven't taken that into account, right? Yes, there can be, let me back up. There are any number of errors that can occur on a link, and a logical link, not necessarily a physical link. I mean, they all occur on a physical link at some point. But at somewhere in the logical link between point A and point B, the two endpoints in the conversation, any number of errors can occur. Those errors typically have at one level, the errors can be one of two classes. They can be transient or they can be recurring. If it's a transient error, odds are there's going to be a checksum failure, a checksum disagreement at the receiving end. It's going to send a NAC back. We're going to resend the packet at the sender side, and it's going to arrive okay, which is what we're indicating here. If the errors are permanent or they're regular, recurring, then we can get into, as I think you're pointing out, Nathaniel, a NAC resend loop. Is that what you're referring to? So typically, this is not in and of itself enough to guarantee reliable transport, is it? We need to do something else. Since we're reading ahead, what would you propose we do?
I think maybe at least we can set a limit of the.
Okay, set some sort of limit? All right. Very good. Yes, you're correct. What kind?
Then maybe that limit is reached, maybe the next time or after some time we can repeat this process.
Say that again in a different way.
Maybe the limit is reached. Maybe we can repeat this process after some time to have a check whether it can succeed.
So, if I understand you correctly, you're suggesting a time limit.
Both. First, there will maybe a count limit. So we should make this process not into endless loop.
Excellent.
So
Excellent.
for example, maybe 10 times or 100 times. After that, maybe. But if that limit is reached, so maybe we should stop and wait for some while.
Excellent thought. Everybody understand what he's saying? Because the possibility exists, and this is going to be like RDT 3.8 or something. Because the possibility exists that we get into a NAC resend loop. We want to set some sort of, where's the best way to place to do it? Some sort of limit. Yeah. Okay? And there are, by convention, okay, logically there are two types. There can be a count, as Nathaniel suggested, or there can be a time limitation. Do, 10 retries and then abandon. Do a retry sequence for 250 milliseconds and then abandon. Typically, what you see specified is something like this. Retries equal, let's say 3, 2. Could be any number, any set of numbers. This number is a count of retry attempts, okay? This is a count of sequences. So get into this sort of loop condition, this recovery condition, do 3 attempts, and then repeat the 3 attempts 2 times. And that's typically how it's specified. And this, in effect, this second ordinal winds up being a time parameter, because each retry takes a specific amount of time, specific number of milliseconds. And what you do by specifying the second ordinal is say, do it for this long, under the assumption, you know, when you're setting it up and you're specifying that second number, you're deciding what to put in there, you know exactly how long a retry sequence is going to take. You know exactly how long it takes the chip to actually take a packet of a certain size, and you're going to know the size, and put that packet on the wire and send the entire thing. And then wait for a response back. Now, the reason why you don't specify a specific time is because at any location between points A and B, client and server, there may be any number of systems in the middle. It's not going to be a point-to-point link, although that's where this convention came from. So you can't directly specify a time limit because you have no control over, nor do you have any way of estimating the number of intervening hops there are in the circuit, in the connection. And between Olivet here in San Francisco and my house, my home in Fremont, at any given point in time, there can be either 2 or 6 or more hops. And everybody understand what a hop is? Hop's an intervening router. This, if you'd gone in and you'd done your dig, one of the things you would have found out when you're looking up the DNS routers was you'd have found the hops necessary just to resolve the name. So you have no way of predicting with any degree of certainty the number of intervening hops. So you don't want to specify a time, because you don't have any control over that. You can't accurately predict that. So what you do is you provide a repeat number. This is attempts, and this is the number of times to repeat those attempts. And by specifying it that way, you take into account whatever the current delays are in round trip time because of the state of the network. And it works no matter what the actual physical path is that's being taken by the data. Is that clear? So you're absolutely correct. Absolutely correct. But we're not going to do that yet.
Excuse me?
We're not going to do that yet.
Oh,
We're saving that until later, when we make things really hard. Okay? Any questions? And there's all kinds of stuff. Oops. Oh, fudge. All right, let me try and figure out where we are here. So, oh,
break
look at that. Come on. Oh, darn it. This is Microsoft's problem. It's not your instructor.
Do you want to take a break?
Is it time? Oh gosh, it is time. Okay, take a break.
Mhm.